Okay, so our speaker for today for the math interest group is Mark Edelman, giving a talk on Wolfram's kind of science. He's given a number of talks, interesting talks for the old guard in the past. One was on determinism and chaos that illustrated the dilemma that comes about between an exact algebraic solution and a numerical solution on a computer. Another was on 1D and 2D error correcting codes using parity check. The third was a mathematical model used for disease propagation, and it showed what level of vaccination rates are needed to get a level of herd immunity, given the reproduction number of the pathogen. While this applied to the then current measles outbreak of unvaccinated children, it was prescient to understanding the dynamics of the upcoming SARS-2 epidemic. The fourth was an easy way to understand Shannon's information theory concepts. So now he's found something very interesting for today's talk with Stephen Wolfram's unique approach to understanding physics based on a lifelong career in mathematics and programming. I also like to mention the word Wolfram happens to be the chemical name for the element tungsten with the symbol W and atomic number 74, in case anybody didn't remember their chemistry. So Mark has spent his career in various engineering work. So please welcome Mark in giving his talk for MIG on Wolfram's kind of science.
Thank you very much. Let me start to share my screen and we'll get this going. All right, and let me just arrange my screen. Okay, now I think I'm good. So today you're going to hear about a distinguished scientist who is active today, whose work is unique and controversial. It has to do with computing and physics and math and a new path for scientific discovery. This is going to be a lecture. It'll take most of an hour. I have to present it this way because the topic is big and it's also unfamiliar to most of you. You need a chance to hear some of the details and also the general significance. I can't cover everything, just highlights. I'm telling you what I've learned, so I'm not infallible. And I'll give a perspective on the larger issues. And as Walt suggested, if you have a specific question, and you need clarification or something like that, please raise your hand or interrupt, and Walt will help me to notice that, and I'll try to clarify. If you have something general to say or to ask, save it for the end, and then we'll have the general discussion. So I'll be talking about Stephen Wolfram and his project to improve the physical sciences. Please remember that I'm telling it, I'm not selling it. I do think it's important. Wolfram has studied what are called simple rules, which are algorithms. He proposes that rules like them underlie and unify physics. But he has a larger concern, which is how to deal with complexity, which I will describe. He prefers a computational view of the universe, and I'll talk about that. And he recommends a new paradigm for research. What I'll describe reflects a particular perspective on math and science. Here's the scenario that we will start from. The physical sciences are tightly bound to empiricism. Ultimately, all the content must reflect or predict observations. When science fails to do that, it needs improvement. Now, math is not strictly a science, but a creative art with a strong discipline of consistency. However, it is possible to do exploratory, empirical math through computation, and that's the kind of math we'll talk about. Now, today, physics in particular has some deficiencies. They're partly issues of ignorance or incompleteness, and partly of inconsistency. Regarding ignorance, physics still doesn't include everything. Dark matter is a good example, still mostly unidentified, even though it makes a large portion of all matter. Black holes, they have some theory, but the problem with them is that they're partly outside our universe. In other words, they're partly exempt from physics. Regarding inconsistencies, the problem is that some of physics and math are not in harmony with each other. I would put randomness at the top of that list. It seems to say that there are events without a cause, things that just happen. We use the mathematical tool of probability to deal with it, but probability has no physical meaning. And then there are those unnatural abstractions that are used in physics, such as infinities and continuity. Neither of those concepts has a empirical basis. And we know that fundamental theories in physics don't always work together, as in the example of quantum theory versus gravitation. And finally, physics fails to master all of its scenarios. When the equations can't be solved, physics more or less falls flat. Many systems are just too complex to be solved, including ordinary chaotic phenomena such as turbulence. This is when the physicists wave their hands and they say that phrase, in principle, there is a solution. Complexity bedevils physics by going against the grain of the traditional reductionism. So it's all from this context that Wolfram's ideas arise. Now let's talk about Stephen Wolfram. He's from Britain, born in 1959, the son of Jewish refugees. He was a child prodigy and a rebellious one. He went to Eton and Oxford, didn't graduate either one of them. And yet, as a teenager, he was researching particle physics, and he wrote an important paper. He went on to Caltech for his PhD, which he did get. He had a Fulbright fellowship. He was in the Institute for Advanced Study in Princeton. He was at the Santa Fe Institute. And there's much, much more. But all this time, he has remained a maverick. Wolfram's interests evolved from particle physics into complex systems and then into computing languages. He founded a journal. He left academia to start a company and develop Mathematica, which is what's called a computer algebra system. It's used today by scientists around the world, and it has made Wolfram a billionaire. Yet he's continued to be an intellectual. His famous book, called A New Kind of Science, is from 2002. but the project is still going on. We'll call it NKS, as he does. NKS, the book, is 1,200 pages. It's surprisingly readable because Wolfram writes in simple, clear sentences. The book and the project are accessible on the internet, where you can even set up some of your own tools to replicate some of his work. Even though Wolfram self-published the book, it turned out to be a bestseller. As the New York Times mentions here, the theme of the book is that nature runs on simple computational rules. Now, let's dip into NKS to see what that's all about. These rules are also called automata. You've all heard of John Conway's Game of Life, which is a two-dimensional automaton that has interesting behavior. Here are some terms that describe an automaton. First of all, it manifests rules or constraints. That means it works in a defined way, such as by a formula or a table. A rule is something that applies all the time, creating a process. In computing, that means iteration. So we're speaking about an algorithm, which may be a program. The result of each step is called an outcome. And when you add them up, they become a behavior. An automaton has a structure, which we can look into, and it may also build a structure. And of course, it's autonomous because you set it up with an input and then you let it run. And finally, there are many possible rules or automata. So Wolfram calls his automata simple rules, and he asks the question, what can they do? So again, what is a rule? It's a constraint on a process. It says the process can only go this way. When the rule is applied, there's a change, an outcome. If the rule keeps going, we get a behavior. Think of the rule as a law in a little universe. Let's explore one example of Wolfram's simple rules. Now, this rule operates in a one-dimensional universe made of little cells. You see the row of cells here at the top. Each cell has two properties. It has a location and it has a color, black or white. This particular rule that we're looking at controls the color of the cell according to the starting color and the colors of the adjacent cells. But the rule applies to all cells all the time. Let's focus on the three cells under the bracket that you see. They are white, black, white. And you could, if you want to, represent that as 0, 1, 0. The three cells together make what I call a case, and the rule will apply to that case. So these three colors will be used to determine the outcome for a cell in the middle. In this case, the outcome is white. I wrote next to it a sort of pseudocode to represent this case, just to show you how you could program it. Now the rule has to apply to any three cells. 0, 1, 0 is just one case. So you know that with 3 binary digits, there are 8 possible cases. Each case will have its own outcome. So the rule needs to cover the 8 cases, and each one could be specified in a code. It's easier, though, to show the rule graphically. Here are the 8 cases with their outcomes. The graphic makes up the complete rule. And you see that the case we examined just now is one part of this rule. Now we need some notation, and Wolfram did something clever about that. He standardized the order of the cases, always starting with all black on the left and ending with all white in this particular order. So this way, the top row in the graphic will always be the same. Only the outcomes will be different for different rules. Therefore, you can make a notation just by using the outcomes. And you could represent them as binary digits, representing black and white. And I've done that. Now these digits are an ordered list. They don't make a number. They're not a number. But we could pretend that they're a number and read it in binary. And if we do that and translate it to decimal, it's the number 90. So that means that this particular rule is rule number 90. That's how we name the rules. Now, there are many possible rules. In fact, since each rule can be represented by 8 bits, that means that there are 256 possible rules of this kind. Now, it's always a challenge to introduce all this notation. So before I go on, does anybody want more explanation of these details? Please ask. I see in the chat there's something. Subscript 0 represents a time before the subscript 1. Well, yes, that's what it represents. No, I'm sorry. I misspoke. My notation in the little pseudocode is I for initial or input, and O, it's not a 0, it's an O for output or outcome. So you have input and outcome. That's how I wrote it, just to help you visualize. Are there any other questions? All right, we'll go on and we're going to use this notation. So now this rule 90, we're going to see the behavior of this rule. So here it is. And remember, we're starting, just for this illustration, we're starting from one black cell. And at the top, you see the rule again. And then we have the top row. In the 3 rows, the top row is the input, which is one black cell. And then there are 2 rows of outcomes. So just looking at the first row of outcomes, the arrows will show you how the rule is applied. On the right, you see the gray arrow, and it shows that under this rule, when you have all white, it just produces more white with no change. Now the gold arrow shows the case that we already saw on the previous slide. Starting from white, black, white, the outcome for the center cell is white. Then you have the red and green arrows, and they're showing what happens to the cells that were adjacent to the original cell. And as it happens, they both turn black. So this is how we get the outcomes in the first row of outcomes. And then we do it all over again for the second row of outcomes. And you see it there. And you see a little pattern that's forming. So what happens if we continue? Well, here we have 5 steps. And the pattern becomes a little bit more complex. Well, where will it go in 500 steps? Now it gets interesting. What can we say about this rule's behaviors? Well, we can observe a variety of behaviors. We see that bits or cells can get copied or deleted. That is to say, the black can get deleted, becoming white, or it could get copied. We see that bits move across the one-dimensional space, and that's communication. We see in the pattern, we see self-similarity, which is nesting. You see little patterns inside of bigger patterns that are the same. We see regions that are forming, such as the empty areas. We see some complexity here, but we also see symmetries or invariances. We see self-organization, making an interesting structure. And of course, we see regularity, so that this outcome, this pattern is certainly predictable.
Mitch Erickson has something in chat. He says these 3 cells of Wolfram are curiously parallel to DNA and RNA triplets. The 3 nucleotides in a row form a codon, and each codon encodes a specific amino acid. So
yeah, well, and that means that if you wanted to represent DNA code, you could do it using some of this type of notation. Also, it's not accidental. I mean, Wolfram's intention was to make a model that would illustrate something that could be happening in the physical world. So he said, how do things work in the physical world? Well, you have an object and you have things that are close to it, and those are the things that affect it. So he made rules that reflect this fact about the physical world, and he made them as simple as he could think of, and this is what he came up with. So it's no accident that it has something to do with the real world. So you've seen what one rule can do. We said there were 256 rules. Some of them are equivalent, such as exchanging black for white or left and right. So I believe there are 88 unique rules. So in NKS, Wolfram takes all those rules and he explores their behaviors or their capabilities. Here's a sample. Some of the rules are trivial and the behaviors can be very simple, as you see here. But some of them make predictable patterns and others look irregular. These are all starting with one black cell. But some rules behave differently. This is rule number 30. And you can see that it's asymmetric. It turns out to be a non-repeating pattern, which Wolfram tested very thoroughly, and he found it to be reliably random. So that's another behavior. It's important to have a source for randomness. You know, in traditional physics, there really is no source for randomness. So that's something to think about. So here we have randomness on one side. Are outcomes predictable? Well, we saw randomness, which is not predictable. But here's a rule 110, and it doesn't look random. On the left side, we see considerable regularity, and on the right side, we do not see randomness, we see something. What is it? Well, we have to follow the rule to find out. And if we do that, here's 3,000 steps. Now, this illustration is in two panels. You start on the left panel at the top, and you follow the rule going down, and then it continues on the right-hand side. And after 3,000 steps, the pattern on the right edge still doesn't show any sign of repetition. So some rules have a very long evolution. Now, up to now, we started with one black cell. What if we begin with a pattern of black cells? They could be random, or they could be the output from another rule, or from the same rule. The resulting behavior could get interesting. What if we go further and we think of the starting cells as data? So here on this slide, just to help you visualize, I have some random starting cells, and I've applied a few different rules which are shown. And you get various kinds of results. In this case, I'm illustrating results which stabilize. Now I'd like to show you an animation. This is rule number 110 again, and I'm showing it how it processes data. The data is at the top, and the outcome is at the bottom. And you see how how each case in the rule is applied one at a time in this animation, producing the output. So what you have to visualize is that all these outputs are happening at the same time. Okay, the rule applies to all the cells at the same time. But we are seeing it in sequence to make it easier to comprehend. So there you go. Does anyone have any questions about what we're looking at?
Mitch
Okay.
says quilters would love to use this in their designs.
Yeah, well, maybe they do. Okay. So let's stop here and say it out loud. All rules compute. The behaviors of simple rules are also computations. What's a computation? Well, it's just a rule operating on an initial state to produce the next state. So if a process obeys a law, then that means nature is computing. Now, does that mean that the universe is a computer? Yes, it does, in a way. A set of rules could make a model universe which could run on a computer. So what's the difference between reality and computation? It's a question that people ask all the time. The difference is in you, the observer. To you, a computation is only a representation of something. In your computer, you see representations. But if your viewpoint were from inside the computer, that would be your reality. It's like the difference between planning an automobile trip and driving the car. At any rate, all rules compute. Now, the game of life was later proved to be equivalent to a Turing machine. Now, you know what a Turing machine is. It's a process by which, with the right inputs, anything computable could be computed. It turns out that Wolfram's Rule 110 and some other simple rules, which are only one-dimensional, are also equivalent to a Turing machine. And if we remove some constraints, the possibilities are vast. For example, we could go up from 1 dimension to 2 dimensions or more. We could allow shades other than black and white. As we will see later, Wolfram expanded his exploration beyond the original simple rules. But the lesson here is that computation only requires simple rules regardless of complexity. Well, didn't we know that? We did, because if you look inside a computer, you find that everything it does is made out of simple operations. So we already knew that adding complexity to the machine or the program doesn't change anything fundamental. So that's the world of simple rules in a nutshell. Let's review. Wolfram designed his rules to be about as elementary as they can be without being trivial. And yet they have complex behavior. Simple rules working together would have unlimited complexity. Also, they're sufficient for computation. So what are we to make of this complexity? That's what NKS is confronting. His hypothesis is that the complexity of the physical world may be best represented as computations, which reduce to simple rules. And from there, Wolfram has some things to say about complexity when it's looked at from a computational perspective. First of all, his whole project rests on the fact that complexity is not exceptional. Therefore, it shouldn't be seen that way in physics. You know, there's a tradition in Western science that says that nature prefers simplicity. All the greats have said it. Galileo said it. Newton said it. Einstein said it. Well, of course, they said it in a certain context. Wolfram is reminding us that science focuses on whatever simple laws emerge. The laws are found, and then that's what we focus on. And that's what the great scientists were talking about. But in nature, you don't have one law at a time. and you don't have controlled experiments. Instead, you have complexity. And complexity is natural, and it should be integral to all sciences. The simple rules might provide a way to make that so. Wolfram's second principle is irreducibility. It means that for many rules, there are no shortcuts, no solutions. Now, in the physical sciences, we try to reduce a problem to equations, and then we solve them in order to predict the outcome. Now, what's an equation? It's more than one thing. Of course, it's a statement that two quantities remain equal under changing conditions. So it's a statement about an invariance or a symmetry. But in addition, an equation is a prediction when we solve it. It's a shortcut. What's a shortcut? It's something that takes you to the outcome without going through the process. So let's say you want to know the sum of the integers 1 through 100. So you could add them up. But there's a formula, and it says the sum equals n times n plus 1 divided by 2. So you use that shortcut, and you get the answer. And the answer is 5,050. You didn't go through the process. What Wolfram is saying, and it's not new, he's saying that many processes cannot be solved with a formula. There's no shortcut, no condensed predictive model for those processes. Some of the simple rules are like that. If you want to know the outcome after 100 or 1,000 steps, you may just have to execute them, see what comes out. And if we remove any of the constraints on the simple rules, a lot more of them will have no shortcuts. But today we have a tool for that situation. And that tool is the computer. We use it to simulate the simple rule and calculate the steps one at a time without prediction. That's what Wolfram has done. He's not applying a hypothesis or a theory. It's more of an experiment. It's empirical. In a way, this approach is closer to nature because nature computes and nature doesn't make predictions. So here's what Wolfram is suggesting. Traditional physics wants to make simple models and solve their equations. It can't handle natural complexity. But with our new abilities in computation, we have a different tool which can run complex models to gain understanding. We already do that, for example, in weather prediction. And it's worth mentioning, although Wolfram doesn't get into this, that machine learning can be applied to complex models in order to discover more about their behavior. Wolfram's third principle is called computational equivalence, PCE. Now, this principle is radical and it's challenging. It says that beyond a simple level, all complexity is fundamentally equivalent. This is a qualitative assertion about computation. It's based on the fact that the complexity of a rule doesn't correlate with the complexity of its behavior. Instead, everything reduces to simple rules and can be explored by computation. So let's try to appreciate that a little bit. How do we estimate complexity? It goes something like this. If we can't predictively model a behavior, we find it to be complex. So it's the power of the mind or the model versus the problem. It's relative. If we only compute the way nature does, without any shortcuts, then more or less complexity doesn't matter very much. To understand this better, let's try using metaphors and a little bit of role playing. So first, imagine yourself as an ant. You have a very simple mind and a limited memory. Not much information ever accumulates in your mind. You don't experience complexity. You just react to a succession of simple events, one at a time. Your world is simple. Now let's take a second case. You're transformed into a skilled mathematician, like some of us here at this meeting. Some of you, not me. You easily figure out things that stump others. But you also find problems that your math cannot solve, or that take too long to solve. So you perceive a complex world. Now a third case. You become a personification of computer technology. Every year you get more capable. 10 years ago, there was a problem that was so big, it would take you a century to simulate it. Today it's easy. And today's complex problem will be easy next year. So complexity is not inherent in a system. Rather, it's relative to the observer's capabilities. This is what leads to the PCE. It says that for many purposes, different degrees of complexity are not fundamental. It's not a quantitative statement. It can't be. It's just that more or less computation doesn't matter very much, because all over nature, there's computation at every level. For example, fluid turbulence is extremely complex, yet it's very common, and it's a computation performed by inanimate objects, molecules, using simple rules. It's just what happens when a lot of simple rules are working in the same place. So in the world that Wolfram proposes, computation is universal. Complexity is relative. And such things as equations apply only in a minority of real phenomena. The rest are irreducible. But if you set a computer to work on them, you can find out their properties empirically. Complexity, not simplicity, is natural to the world, and shortcuts are not usually available. But we can still do computational experiments. Wolfram suggests that in the age of computation, we have a tool to explore the world as it is. But that sort of endeavor requires adding a new paradigm of research, allowing computation as an empirical tool. The computational paradigm takes the view that reality mostly doesn't resemble equations. It resembles computation because it is computation. Computation is performed even by inanimate objects like molecules. All the laws of physics are rules or algorithms for computation. So if the world is computation, it's all a computer that we live in. Now, if you thought about computers only in terms of electronics and numbers, you have to upgrade to a bigger vision in which computation is fundamental, and we and our ideas are just passing patterns. In a computational universe, we have to recast the basic concepts. I won't get into it in detail, but consider this. If it's all computation, then in between the operations is any time passing. And inside of a computer, inside of a computation, what's the meaning of space? That's something to think about. In a computer, you can't chop something into finer and finer divisions without limit. Ultimately, computing consists of indivisible choices. Choices are not continuities. The fundamental discreteness of computing also means that there are no infinities. Now, today in physics, infinities, many physicists think that infinities should be banished. Our current ideas about cosmology agree with that. The universe is finite, and so is everything in it. So the computational universe occupies a different conceptual space from traditional physics. This is why Wolfram argues for an exploratory endeavor as proposed in NKS. He actually wants projects like his that start with a system of abstractions, like his rules, and research all the possibilities. He coined a term, ruliad, to mean all the possible rules. Ultimately, it could amount to a recasting of physical laws in terms of rules or computations instead of continuous equations. It would be a new language for physics. The most basic objects in physics might be rules rather than particles and forces and dimensions. Computational interactions could be the best models of reality. There would be less emphasis on solving and more emphasis on simulating. And that's Wolfram's program. He proposes computation as an empirical tool, like a telescope, to discover the computation in the world. It would lead to exploring phenomena that traditional physics has not tended to focus on. What Wolfram calls the ruliad is huge, and no doubt there are discoveries there. He thinks that they would advance science and technology. Now, the NKS project has not become mainstream in physics, but Wolfram is undeterred. As a wealthy intellectual, he has the same freedom that some of our famous scientists had in the 18th and 19th centuries. And as a maverick, he doesn't seem to care much for today's consensus. His vision is long-term. Since the NKS book, he has expanded his project beyond binary rules beyond one or two dimensions and actually beyond numerical abstractions. His biggest pursuit now is in what are called hypergraphs. You see on the slide an elementary illustration of a hypergraph. You see nodes, and nodes could be anything. They're just any kind of object or item. They don't need to have any other properties. And you see connections between the nodes. Connections are relationships. They form networks. And to understand hypergraphs forming networks, you use concepts about spaces, dimensions, topology. These are all fields of mathematical research today in which computation is being used. So what Wolfram is doing is to explore the ruliad, the rules that could apply to these hypergraphs. He thinks it's suited to the nature of physics. In essence, he's suggesting that simple rules may generate the complex networks of matter and energy that we experience. In fact, in 2020, he published a 450-page sequel to NKS. And this year he's busy creating an institute to continue the work. Wolfram claims that rules based on hypergraphs have been able to replicate some of the basic physical laws. He just wants the field of physics, like other, if not other fields, to recognize this new approach and to exploit it. All along, the physics establishment has been resistant. After reading some reviews and some articles, my feeling is that there's fault on both sides. Here's what the New York Times reported. Researchers ignored and derided his work. Here's Scientific American, no less, misreporting the project as a theory of everything. It's not. Wolfram's project is not a theory. It's a proposal for a paradigm shift, a new conceptual language, and a new kind of research. Here's the accusation of no testable predictions. That's a deliberate misunderstanding. Often Wolfram doesn't get respect. Prominent physicists like Freeman Dyson, Steven Weinberg, Roger Penrose, they've insulted him with ad hominem attacks. One reason for their disrespect is that Wolfram disdains the strict tradition of peer review. He's still a maverick and a gadfly. It might be worth mentioning, though, Charles Darwin didn't exactly get peer review before he published. And there are many other examples. Wolfram also has speculated a lot in his book. He imagines the possibilities. Now, some of your best-selling theoreticians, people like Dyson and Weinberg and Penrose, have done exactly the same thing, but they hold it against him. So here's my bottom line about Wolfram's work. He's an idealist and also unwilling to adopt mainstream methods or manners. He's correct that physics in particular is stuck in some ways. And in response, he's proposed some new approaches and tools. The establishment reaction, on the whole, is based on not invented here. A stronger criticism is that Wolfram doesn't present evidence for his proposed framework. And his answer to that is that he's proposing tools and studies, not advocating a specific theory. There's a conflict going on between institutional science and science as a private enterprise. Wolfram is in the private enterprise, and he has the means to do so. In fact, he may be unique as an intellectual billionaire. He truly seems to care more about science than about money. That doesn't make him right. But his ideas are honest and they have potential. Thank you very much, and I hope that you have reactions, comments, and questions.
Okay, and very nice Dilbert strip there. We'll open it for questions. Has anybody actually taken some time to look at the one article that was sent out in the email, which kind of goes into how he thinks that physics can be sort of rewritten according to his paradigm? Please unmute yourself if you want. Either raise your hand or unmute yourself. Jim Fleischman.
Yeah, I did not read the article, but one of the things that caught my attention is I happened to be about halfway through reading James Glick's book on basically the biography of Richard Feynman. And interestingly enough, Feynman was the advisor to Wolfram when he got his PhD at Caltech. So they knew each other quite well. And Glick is also the guy who wrote the book Chaos, who detailed back in the 1980s the whole, he was the first one, I guess, to popularize the concept of complexity in that book Chaos. And I was just amazed by how all this stuff fits together, and I can certainly see how many of the modern day quantum physicists would have objections to what Wolfram is doing, because it basically upends the massive investment that they've made in all these calculations and methodologies that have been developed over the past roughly 100 years. He's kind of turned it on its head. So I would just, first of all, Mark, I thought that was a fantastic presentation, and it was incredibly concise, to the point, and I greatly appreciate, because I'm sure you put a hell of a lot of work into putting that together.
Thank you very much. I did put a lot of work into it because I was enthused about it. I like to get to the bottom. That's where the big ideas are, at the bottom of everything. And that's what Wolfram likes to do. So I could relate to that. And you know, his ideas, his models, his idea about simple rules isn't meant to contradict physics. It's meant to reimagine it. So he wants to be, he doesn't contradict any theory in physics. He wants to write the theory a different way, model the theory, turn the theory into a model, turn it into computation. Walt, why don't you be the one to call on people?
Yeah, okay, we have a number of raised hands, so I'm gonna call them in order. Poppy, you're next. Please unmute yourself.
Yes, it's a fantastic presentation, Mark. I I was I I think you read a lot. Uh, the abstraction. Where does Wolfram get his money to do this kind of exploratory research all on his own? It's essentially challenging the establishment.
Where does he, you're asking, where does he get his money? He got it by making money on Mathematica.
Oh, okay.
Yeah, yeah. It's amazing. I was very surprised to learn that he's a billionaire. I didn't think that, one big product like that could make somebody a billionaire. I mean, of course, we have our internet billionaires, but they're doing something different.
Yeah.
I mean, he's making a product, and but it's used around the world, and it's expensive, and he's getting that money.
Okay, so
Um,
he
and I
has
guess he owns most of the. I mean, he doesn't have a public company as far as I know. He owns it.
he owns it himself. Okay, in the Mathematica. So
Uh,
that started off with something more simple, I think. I was trying to remember.
So how many people on the call have used Mathematica?
I did.
1, 2, 3? Because when I was in academia, people were using MATLAB, for
Yeah.
doing homework projects and things.
Yeah.
But I never
I
really had.
use extensively MATLAB. I use it extensively for simulation.
Okay, so let's move on to the next. Mitch Erickson, you're next. Please unmute yourself.
Yep. Hey, Mark, echoing everybody else, great presentation and a lot of hard work behind it. You didn't toss this off starting at 8 o'clock this morning, clearly. um, anyway, I'm just amazed that I'm not a physicist, et cetera, but I'm amazed. I've heard of guys like Feynman. I've heard a lot of the luminaries in the world, and I just never had heard of Wolfram before you announced this topic. So, kudos to you for broadening my horizons. I'm a big fan on getting my news feeds every day from something called Axios, Axios, and I think it's a really good thing. And they are big fans of something called smart brevity, if I can get that right. And I just got the book on it yesterday, but I think Wolfram could probably use to learn something about smart brevity with his 1,200 page and 450 page tomes. But that's an aside. We've been stuck in physics for what 100 and some years trying to figure out the unified theory and get gravitation in with the other forces. And string theory seems to have been stuck for, I don't know, 50 years. So the notion that we need to rethink the way we look at these problems is obviously a good one. Whether he's got the right thinking or not, not within my level of consciousness. I just want to also point out that when we think about the way the world works and so forth, over all of our history, we've relied on divine guidance, skyhooks, a variety of different crutches to explain stuff we can't explain. It used to be we had to have, God, ran uh, the levers of the universe, the Wizard of Oz, and we come up to today, and people invoke various magical things for before the Big Bang, outside of the current universe, etc. And it's just interesting that, here we are, and here he's thinking about ways to get rid of yet another skyhook in our lives. So again, thanks, Mark, for doing it, and it's just an interesting uh, way of thinking about the world.
Well, the people could accuse Wolfram of really doing the same thing as everybody else, just making another thing fundamental, and then you have to ask the question, well, why? But I was thrilled when he confronts the problem of non-physical things being in physics. That really got to me. I mean, every physicist would agree that there's no actual infinity in physics, and yet, it's in some of the math. So they would say, well, the math is only a tool. Okay, you can go with that. Then there's continuity. Nobody knows for sure, but in quantum physics, there is no continuity. You can't find it anywhere. There is no physical evidence of continuity anyplace. It's just something we assume, and it's convenient for mathematics, but is it real in physics? And then, there are the mysteries of time, which are definitely not solved at all. What is time? Why does it flow? How does it work? It's absolutely not explained. Then we have the things that are actually physically outside of physics. And the black hole is the primary one. I mean, I don't know if anybody's given this much thought, but, the black hole exists in our universe. But in the center of it, there's what they call the singularity, which is a cop-out, because at the singularity, there is no physics. There are no physical laws that apply. So it's outside of our universe.
Another skyhook.
Yeah, sort of. I mean, it's not explanatory. It's the opposite. It's a thing where we just come to a dead end and we say, okay, that's where it stops. Well, you would like physics to have a physical explanation of everything. You'd like physics to be about physical things, right? But infinities, continuity, and also randomness have no empirical existence. I mean, Jim the statistician would say to you, well, of course randomness has an existence. Yes, it has a mathematical existence, but it does not have a physical explanation. And, sometimes we confuse math with reality. Maybe Wolfram is doing that too. Maybe because Wolfram is mathematizing everything in his way, using the automata. Maybe he's just as guilty as everybody else. We are.
Okay.
I just want to finish up, and I apologize for hogging the microphone here, to go to the other opposite extreme of explaining things. I'm going to go back to the 1960s when Bill Cosby was a good guy and remind you of the question of why is there air? And his answer was to blow up basketballs.
Well,
okay, now somebody else can go back to the seriousness.
Okay, Thad is next. Would you please unmute yourself?
Right. Yeah. Hey, Mark, wonderful talk. Never heard of his work, but it's kind of interesting the way that his patterns develop. And And you can have a variety and a great magnitude of variations. So I'm assuming what he's trying to do is find something that has an output of the way that it does the calculation like you demonstrated, to try to model something physically. Has he been successful in finding at least one thing that he can model?
Yes, he claims to be, and it's disputed. I can't say that the dispute can really be resolved. I don't know. He claims that he has a way of using his automata to model or agree with or simulate some basic physical laws, including some of quantum mechanics and including Newton's laws and including relativity. His claims, some are sometimes ridiculed by certain physicists who say, no, it's faulty. But then there are others who say it's not that it's faulty, it's just that it's the wrong thing to do. I don't have the answer. But the immediate answer is that yes, he claims that he's done that much, but he does not claim that he has any new theories of physics. That is not his work, and that's a misunderstanding. The idea that he's making a theory of everything, that's completely false.
So is he doing this kind of like randomly looking at the results and trying to match what occurs?
Nothing he does is random. This is the most methodical man you could ever imagine. And if you go to his website, you will very rapidly see that. This is a guy who is absolutely methodical and disciplined about every single thing that he does. And by the way, his self-published book is beautiful. I mean, it's so beautifully made and printed and designed. He's not satisfied with anything less than the best.
All right, thanks.
Okay, the next person is Jim Landwehr. Would you please unmute yourself?
Yeah, thanks. Maybe it's a slightly different version of what Thad and Mark were just talking about. And Mark, it was great talk. Thanks for putting all the work into it. It's sort of my simplistic notion of science as well, the theories of science as opposed in conjunction with the observations, is that you have a theory that explains the existing data and you say, great, and maybe it's a good theory. And then somehow if it makes a prediction about something that hasn't quite yet been observed, and if that prediction turns out to be correct down the road, that is, data fits that prediction, then everybody says, oh great, that's a good theory, that's better because it predicted something that the previous theories hadn't predicted. It may not be the right, quote, right theory, whatever that means, but at least it's a better theory than what we had because it predicted something new that hadn't been either observed or predicted by the previous theories. And so my way of phrasing that question is that within the mindset of what Wolfram sees, and is it conceivable that his approach would predict something that hasn't been observed, not whether it has happened, but is it conceivable that he could predict something that has not yet been observed? And if it were observed, then people might say, yeah, this is a better theory than the previous one. So that's one version of the question. The second thing is just this randomness thing. Sort of my view on randomness, just completely separate topic comment, is randomness is always conditional. It's conditional. Randomness is a notion that applies conditional on what you or whatever the body in question is know. You know, if I put a coin down on the table and cover it up, I put it down, I know if it's heads or tails. It's not random to me because I know. But if you walk into the room and my hand is over the coin, to you, it's random because you don't know what it is. And so you've got a 50, you might say, oh, well, Jim always does heads or Jim always does tails or whatever. But apart from that, you don't really know. So it's random from you, but it's not random for me. So my notion of randomness is pretty much always that it's conditional on whatever the state or the observer or the knowledge is. So whether something underneath in physics is truly random or not, I guess that's kind of like it's moot. It's conditional on what we, what we know.
Yeah, that is a great point. If you, I hope I get this right, and maybe someone can correct me if I get it wrong, and that's okay. My understanding is that in physics today, there is randomness that's inherent. In that sense, it's not relative, but absolute. In our physics, it's only at the macro scale that randomness can be, statistical. At the micro scale, there is a mysterious, unexplained randomness, and that is the gap or the empty spot that I was talking about. For example, radioactivity. What theory says is that the uncertainty principle, which itself has a lot to do with randomness, the uncertainty principle guarantees that every once in a while, any particle can, decay. Or maybe I should say any atom can decay. Any nucleus can decay. Random fluctuations happen, and every once in a while they happen to go a certain way that allows, a neutron to escape from the nucleus, or something like that. So the physicists wave their hands and they say, well, that happens at random, but it happens at a certain rate. And that's, that defines the half-life of an isotope and so forth. And the rate is statistically reliable, so they say, well, that's the way it is. But they've explained nothing, because all they're doing is pushing randomness back beyond physics, because there's no physical reason for it to happen.
So
They're saying it happens for no reason.
My take on that is that, well, I'm not a physicist or a statistical physics physicist. There are such people. I really don't care. From my perspective, or the perspective of the data that I would have available as a statistician dealing with observables in the real world, to me it's random, and whether there's some underlying truth to it, or God is choosing this or that or whatever, hey, that's a different question. It's not really what I'm professionally interested in. But I would like any comments you have on the first part of my comment about the possibility of predicting something that other theories might not have predicted already.
Well, yeah, okay. Let me respond to that. In a way, everything that Wolfram is doing is responsive to that. I mean, he is saying that when something happens in the physical world, it's obeying a law. And the idea of a law is that it's a rule that always applies. And he's saying, how do we model this rule in a computational way? Okay, without using continuity, for example, but using computation. Well, of course, we know how to do it. I mean, you know, you make a spreadsheet and you have more, you add more rows to it, or you make an automaton like the game of life, and you let it play out. We know how to do those things. He's saying maybe nature really works like that. All right. So by saying that, he's actually saying that, yes, he has not a theory really, but a sort of a proto-theory, a sort of a pre-theory that could become a theory that would be equivalent to some of the laws we've already discovered in physics and that we articulate in a different way. So he is doing that. He is trying to do it. But his mission is not to find a new theory that'll become, you know, Wolfram's law. That's not what he's trying to do. What he's trying to do is to reshape the physical sciences in the long view, and let other people make the discoveries. He wants people to explore this thing that he calls the Ruliad, explore all the things that could happen and find interesting things. And then he believes that we'll probably end up discovering that they actually exist. And, you know, that's been the history of cosmology. Black holes being a perfect example. They were discovered first in theory, and then they were discovered in reality. It's a good illustration of it. Okay.
Okay, so the next person that up is John Tomaszewski. Please unmute yourself.
Yeah, hi, great talk. I rated a 5 on a 3 scale. But you know, it brought back some memories of little science fiction things that I've watched. The first one was The 13th Floor, which if you ever like science fiction and like detective stories, it's a great one. And of course, The Matrix, where we are actually not really where we're at. We're in a simulation of someone else's, a higher power of some type.
Yeah.
And all our life is just random, not random, but things that have been set forth by computer computations. I was wondering if you had a comment on that.
Yeah, I do. There's a difference. I mean, in the Matrix, somebody is doing it for making us, you know, by doing it, somebody's programming it. In Wolfram's imagination, you know, there isn't any somebody. We're not being manipulated, but everything is computation. But the computation just happens by itself, the same way that physics does. It doesn't happen because somebody's pulling the strings all the time. The causes are built in. Sorry. The causes are the rules. Okay? The rules are the physical laws. It's just that he's going beneath the standard physics, you know, like Newton's laws. He's going beneath that and looking for something that would explain it at a deeper level, and that would also tie together all the different laws. And he's proposing that a set of computational rules could have that function. But nobody's pulling the strings.
Okay, the next person up is John Maheda. Would you please unmute yourself?
Mark, a fantastic talk, and I cannot thank you enough for giving us here. It opened my eyes. I think, and again, I'm not a theoretical physicist, but I think there's a place for both the traditional physics and his approach. What you get from traditional physics is a certain sense of intuition how things work. It's based on equations, it's based on experience. If you talk to an expert in physics, you kind of know that he's talking a lot from what he's talking is intuition based on his experience with equations, data, and so forth. What I'm concerned about the rules, Wolfram rules, is they may not be intuitive. On the other hand, physics is getting less and less intuitive as we go along. I mean, the particle physics is very not intuitive, and perhaps the Wolfram's approach is a correct one for the sort of non-intuitive physics. So I think there's a place for both. I just don't know whether showing that Wolfram can simulate or come up with rules to explain, for example, Newton's law of motion and so forth, is really going to be a very good example of how well it works, because I suspect that traditional physics is a better way to do that. But when it comes to things that are totally non-intuitive, maybe the rule approach is a correct one. By the way, I find it kind of interesting that Wolfram is basically believes that computational physics is basically the way to go, because computational physics is based on very simple rules, which could be called the Wolfram rules. Now, 1 + 1 = 1 carry 1, or 1 + 0 is 0, and so forth. If you look at a computer, the way they operate with the very simple rules.
Yes, and I mentioned that, and he's saying we should recognize that simplicity and use it. We should recognize that the simple rules produce the complexity that we experience. And he's right that a physics education tends to prejudice you against that, because physics is always trying to find things that are simple. And the meaning of simple is very hard to pin down. I mean, we all know that Newton's laws are relatively simple, but they're only simple because we have a notation that looks simple. Then when you look behind the notation, you discover it's not simple at all. It's complex. I mean, you can write F = ma, but you're not supposed to really. You're supposed to write differential equations. And then you write the differential equations and you discover a lot of times you can't solve them. And, physics seems to be devoted to hiding the complexity behind a veneer of simplicity. And this is one of the strange things about our science. Okay, I digressed from what you said, but you could go on and on, exploring this.
Right. Well, to quote Einstein on simplicity, Einstein said, things should be as simple as possible, but no simpler.
Yes, but the context, what was Einstein talking about? He wasn't talking about the universe. He was talking about physics.
Exactly.
And we should always remember there's a difference. Physics is a representation of the universe.
Yes. But I think there is something to be said about sort of intuition and understanding, which you do get from traditional equations, and I am not sure you would get that from the simple rules.
Yeah, you wouldn't. You have to do the exploring. That's his thesis, that
right.
You won't be able to see the behaviors right away. I mean, some of them you can, but many of them you can't. You have to test it. You have to study it empirically. And he's saying the computer is what we have to do that. So a good analogy would be astronomy. You know, you build a bigger telescope and now you see new things and they give you new ideas. Until you build that telescope, you can't see those things. And so once you see them, then you start exploring what they might mean and you try to integrate it into the things you already know.
Right.
Well, that's what he's advocating.
Okay. Well, thanks again. Fantastic talk.
Okay, I'd like to say a few things. You know, this is with regard to radioactivity. You know, if you think about it, if you have a plane of radioactive atoms, you don't know which one is going to decay next. But I can just see applying some special rule, maybe rule number 54, it'll go through the whole, you know, if you apply it to that grid of atoms, it'll tell you which one is going to decay next.
No,
And
no, it won't. But what it might do, in my imagination, what it might do is give you a generator of randomness, which physics currently lacks.
Okay.
well, and my question with, you know, radioactivity, there's still a question is, what is the mechanism behind it? So whether you
Yeah.
use a rule to do it or some other explanation, there still is, what is the fundamental mechanism that triggers, you know, one atom to decay,
Yeah.
you know? And
And
so,
what we have is the uncertainty principle for that. That's what's behind it. But
well, the
it
uncertainty principle,
still leaves a mystery about the randomness part.
the uncertainty principle only tells you if you want to know the position or velocity of a particle, right?
Yeah, and because of that, in any collection of particles, some of them are going to be the outliers that have an unusually high velocity or really momentum. And because of that, they escape, and that's radioactivity.
Dick Aiken,
What?
you have something to say?
Yeah. First of all, thanks a lot, Mark. An eye-opener talk. I have to think about it a little more to ask a good question. But what comes to mind is, hey, as John says, hey, we have classical physics and regular physics, and we have intuition to say, well, let's explore and figure out some new formula or so forth to describe things. Now, how does Wolfram say, how do we explore all these rules? You have the ruliad or whatever you call it. Is there any intuition that you use to explore finding good rules?
Well, in his book, he contradicts himself. He makes a lot of intuitive statements where he says, I suspect this, or, you know, I think it's going to turn out like this. Those are unjustified. They're just speculations. But then on the other hand, what he's advocating is methodical, empirical exploration of this ruliad. In other words, he's done it for the simple rule that I showed you. You know, he's explored everything that it can do, right? But, you know, those rules were just, you know, to start with. And now he's into these things called hypergraphs, which are more sophisticated. And he's saying we need to explore everything that they can do, everything. You know, not following our own intuitions, but trying all of it, everything, using a computer.
In other words, exhaustive exploration.
Yes, that's what he's advocating.
No.
Well, he says we have the tools to do it. Yeah. So in a way, he's empirical, and he's in a way he's almost anti-intuitive, but he indulges in some intuition too.
So is he using some of his billions to hire postdocs to do these pursuits?
Yes.
Turn the cranks.
Yes, he is.
Yeah, okay.
Yes, he is.
So he's
He-
putting his money where his mouth is.
Absolutely.
Good.
And he's the only one, maybe, who's done that. And Mitch, you wrote a comment here that I don't understand, but it would be interesting to hear from you about it. What you wrote in the chat.
Well, I'm just poking around trying to figure out what's going on, and I started with a Wikipedia that you recommended on Stephen Wolfram and so forth, and I wandered into Mathematica, and there seem to be two websites. One is Wolfram Mathematica. That's based in Urbana and blah, 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 blah. And then there's another Mathematica that's based in Princeton. I don't know anything about it, and three of you guys said you used it. Are there two different Mathematicas out there?
I don't know.
Okay, well,
Yeah.
I
think there are two different Mathematicas. One's a publicly traded company, and I actually have a friend of mine who sits on the board, and I'm not quite sure what they do, but it's some software, but I believe it has nothing to do with Wolfram's Mathematica, although I'm surprised that it's got the same name. I think the publicly traded Mathematica came out of Computer Associates. It was a spin-off 20 or 30 years ago.
Oh,
yeah,
that's
the
interesting.
Mathematica, the non-Wolfram one, the Wikipedia page says they started in 1968, so they've been around a while.
Yeah, well, that would be a little bit, if that was really started then, if that product was started then, that's before Wolfram's time, because he was born in 1959. I mean, he's a genius, but not that much of a genius.
I think now you're bringing up some vague memories. I think there was a consulting thing in Princeton called Mathematica that goes way back, like Jim said, to whenever. So they were using the name Mathematica for some consulting purposes, some people in Princeton, so they may have had the right to continue to use that. And then Wolfram, early in his career, was at UI, University of Illinois in Urbana-Champaign, and that's where he probably got Mathematica going and whatever. So it may be two different sources of the similar name.
Now that I look at the Wikipedia a little bit more carefully, the one in Princeton is in fact a consulting group.
Yeah, okay. That's interesting. Well, for all of you, any of you, if you want to see something remarkable, I can't tell you an exact reference, but if you go on YouTube and you look for Stephen Wolfram, you'll see him giving various talks at various occasions with different organizations. You can look into that, and you're likely to find one where he's standing up at a podium explaining some of his ideas, and he loves to do this, it seems. He loves to talk to young people and encourage them to go into the things he's interested in. And then he pulls out his laptop and he, projects his screen, and he shows you, you see him almost miraculously using Mathematica to do amazing things in a few seconds. I mean, it's the fastest you ever are going to see. He's talking about a problem, and then he just types a few keystrokes, and there it is on the screen. And I know he's not faking it. He's just very, very good at it. and you can watch some of that, and it's really a spectacle.
Okay,
So
we have a hand raised. Griff Smith, would you please unmute yourself? Griff?
Mark, this is the start of what I expect to be a very entertaining day, since I have another Zoom session that's supposedly going to start in another 15 minutes. And then I fit a competition this evening. Thank you very much for this stimulating conversation. I envy you for your ability to express complex ideas in real time so eloquently. Thank you.
oh, well, thank you, Griff. And you know, you shouldn't make it seem like I'm so much better than you or something, because I'm not. Because I remember the presentation you did about touching on Fourier analysis and so forth, and it was great. It was so educational, and it was very clear. So anyway, I guess we're running out of time.
We have one more question from John Tomaszewski.
Oh, yeah.
Actually, it's a comment. I mentioned this before because I love apps. There's an app called Wolfram, and I guess it's a takeoff on Mathematica. It costs about $10, and it has almost every formula that you could possibly want to use. It sets it up for you. So if you want to have some fun with math at a very small expense, look it up. It's again Wolfram, and it's on the in the app stores.
Well, if it uses his name, maybe it's one of his things. He's got more than Mathematica. You know, he also has this thing called Wolfram Alpha, which is sort of an encyclopedic database, I believe. I haven't looked into it really. He's got a few different enterprises, but he continues to, yes, put his money where his mouth is, supporting the kinds of research that he thinks, that he's interested in. And he's starting an institute, which I guess would be independent, to continue that type of work. So there we are. Anyway, I guess we're running out of time.
Okay, we're coming up on 12. I want to thank Mark for opening up our eyes on a remarkable person and his work. And we'll call it the math meeting to a close. Thank you for all attending.